my dear sons and daughters of Bashkortostan, and other participants who are listening to this, a good, very good afternoon to all of you. This arrangement is really very innovative and very useful for disseminating the scientific knowledge to common people and to students, everybody who is interested in this field. As you know that it is the scientific curiosity that is the mother of all inventions, discoveries. So people have been asking, when they opened their eyes, they saw that everything was moving. The stars are moving, planets are moving, and everything. The cars are moving in the street, the leaves are moving, nothing is static. The atoms in our body are moving, there is nothing static in this universe. So scientists ask, is there any law governing these motions? So it was Isaac Newton, over 250 years ago. He asked this question himself and tried to find the governing laws. So he enunciated three laws of motion, which you all know, in the school you studied, and also a law of gravitation. And this explained motions of planets and even motions of rockets, projectiles, and motion of everything around you in the universe. It was a great discovery, and this laid the foundation for what we call modern science today. So it was the beginning of science. Now, today we talk about black holes and wormholes, dark matter, dark energy, and so and so. At the time of Newton, those things were not even imagined, because nobody knew about it. But as I said, it is the scientific inquiry that goes on and on, which leads to new discoveries like these objects that I said. And you will be very glad to know that all these things, especially black holes and dark matter, dark energy, they have been detected, they have been observed. So my point, my topic of discussion should be black holes and wormholes, as it is written there. So I shall try to be very rudimentary, elementary, so that students can understand it very easily. And what can I say? The whole idea is to kindle the interest in their young minds so that they can one day contribute to science and bring glory to Bashkortostan, and that's the whole idea. So this is the topic, just an introductory topic. It is a subject which is in the frontier of science, the modern science today. Okay? For instance, I can tell you, last year Nobel Prize was given for the discovery of black holes. See? So therefore, it is a subject of today. And if you, and in this lab, we work in the lab here, we have a lab named after Zeldovich lab. Zeldovich was one of the pioneers of astrophysics in Russia, and we have named our lab after him. And the lab was inaugurated by Professor Starobinsky, who is a member of the academician Starobinsky, who came here, and he inaugurated the lab. Therefore, there is some connection with great people in science with our lab. And today, I am going to talk about some fundamental ideas of this so that you become very interested. Okay, so going ahead. So this, of course, you can realize that this is Sir Isaac Newton, and you know the story of an apple falling. And of course, nobody knows whether the story is right or wrong, but this is what people believe. And you know the law also, there are two masses, m1 and m2. You know the force between them, m1 m2 by r square into g, which you know very well. In the school you studied it. So everything began with this. Then what did it explain? As I said, it explains the motion of planets around sun. This is sun, and this is the motion of planets. Okay? And it worked for all the planets that you have in the solar system, and the trajectory, the motion, the path of a planet around the sun was very accurately given. But very accurately? No. This is the thing. Actual path is this, not like this. It is a closed path, elliptical path, as you can see. But the reality is that the path is not closed. As you can see here, it is not a closed path. It starts like this, this goes on, and it goes there. The path is not closed. It doesn't come back to the same point. Okay? And this is a fact. Now you could ask why it was not seen at the time of Newton? Because the telescopes were not that accurate. This was observed by Kepler, Johannes Kepler, you must have heard, you must have read. But his telescopes were not very fine, not very refined. Therefore, he didn't see that actual motion was like this. Of course, it is given here in a very enlarged form, but it is not that enlarged. You see, it is just almost nearly this, nearly. Not like this. I am showing it just for you to understand the actual motion of planets around the sun. Okay? It is in an enlarged version. Remember, don't misunderstand me. It is very close to each other. The ellipses are so close to each other. How close, for instance? It is if you wait 100 years on Earth and measure the motion of a planet, say Mercury, which is nearest to the sun, you will find that this change of angle, you see, this change of angle, it will be 43 seconds if you wait 100 years on Earth. 43 seconds, not even a degree, not even a minute. 1 degree. So you divide it by 3600, then it is 1 second. So 43 seconds per Earth century. This is the motion. So the motion is almost like this, almost. You see? I hope you understand. It is not like so as big as this, but this. So you see, there is a motion. But for the Keplerian ellipse, this ellipse, you come back here. You come back exactly here. But here, you don't come back. I hope you understand it. So therefore, Newton's theory, which gave the Keplerian ellipse, what is Newton's theory? You know, F equal to G m1 m2 by r square with a vector, unit vector. So this law, it gave you the Keplerian ellipse. This. But this is, now we see that this is not correct. So that one is correct. Therefore, a new law is needed. This worked for 250 years, but this is not correct. Then came this man. He explained the problem. This was the problem. This was to be explained. Nobody could explain it. There were many efforts to explain it, but nothing was successful. Then came Albert Einstein. He explained it very nicely, but for a price. What was the price? He said that there is no force like this, no force. Can you believe it? Which people believed for 250 years. And this gentleman comes and tells us that there is no force, but everything is geometry. What kind of geometry? Here. You see the Einstein's field equation, don't bother about it now. You will learn it when you come here in our lab. And this is what is happening, that if there is a mass here, let us say sun or earth, whatever, then the space-time four-dimensional network around us is like this. It just gets curved. Now, what is this? This is a net, as you can see, like a fishing net, right? You see it. But imagine this fishing net, which is two-dimensional, right? X and Y. It is not just X and Y, but imagine it is four-dimensional. You have X, Y, Z, and time. Then it becomes a four-dimensional network, which you cannot draw here. Therefore, it is like this. But imagine it is not two-dimensional, not X and Y only, but X, Y, Z, and time. So, as you can see, he says, Albert Einstein, he said that matter curves the space-time. If you put a matter on the, like on a net, if you put a ball, a stone in the net, what happens? It becomes like this. It sags like this. Therefore, this is gravitation. He said that the planets move around these lines. You see? This one. This motion of planets can be explained by this. They move along this line. Okay? It was strange because nobody could believe this, that is this correct? It turned out to be correct. It was a crazy idea at that time, it seemed like. And I also want to tell you that you see here the sun or an object, a planet, and also this sagging. Don't consider them together. This is the cause and this is the effect. So you cannot consider them together. When you consider only this. Don't consider this. Okay? Understand, try to understand it clearly. Consider only the curved space, curved space-time, not the object. So everything that you see around us is curved space-time, something like this, because around us is all four-dimensional. We don't see time, but we live in a four-dimensional world, and our presence is making this. This is a black hole. If it is a very condensed object, high-density object, okay? So 10 to the power minus 96 grams per centimeter cubed. So what happens is, this is actually goes on, and there is a hole here, and that's why it is called a black hole. I showed you, just look at it again. You see, this is a small mass, so it is a small sagging, but if it is a very high mass or high density, then you will find it will fall down, isn't it? If you put a very heavy stone on a net, what happens? The net will tear off. So it falls down. So this is a black hole. Now, the problem with the black problem, or you can say new idea, new discovery, is that if something falls in there, it cannot come out. Even light, you see, it absorbs light. Light cannot come out. Nothing can come out. It can only go in. It's just like a one-way traffic. So it goes in. This is a black hole. Okay? And there is a region beyond which you cannot come. If you are here, you can come back. If you are there, you can come back. But once you cross this, you cannot come back. And this is called event horizon of a black hole. So a black hole is actually, according to Einstein, and which is correct, is that it is a pit that goes on, falls off. Okay? It is stored here. Then, okay, how do you know that there is a black hole in the sky? This is the way. You see, there is a light, there is light, that go from here and it comes to here. This is where we are. This is Earth. So this is a quasar or a black hole, whatever. It comes from here, here, and it comes from here, here. Okay? And so you don't see it here. You see the image. One image is there, another image is there. When you look from the Earth, you see the black hole, not here, but you see it, one image is here, and other image is here, two images. And why there are two images? Because light is bending, you see. It is not going in a straight line. You must have read in the school that light travels in a straight line. No. Only in a region where there is no gravity. But if there is gravity, light bends. As you can see, it goes here and bends to Earth, to your telescope. So you see that you find one image here, another image there, two images. So this is a confirmation that Einstein's theory was right, initial confirmation that you see images. You don't see one object, but you see many images of this, which means light bent. Light was bent by gravity. What was this bending? It is, sorry, you see here, these lines. They are all bent lines. You see these lines. They all are bent lines. It is another version of this is what I have just shown, that light bends. You see, nothing is straight here. Nothing. So this. And this is called gravitational lensing, which is a very hot topic in our laboratory. We have published many works on this. And this is called gravitational lensing. Must understand that we cannot go to the black hole, we cannot go anywhere, not far, but we still want to have the information about the object. The only way to have information about distant objects like a quasar or a black hole, whatever, is only through light, sweat, only through light, the light that is coming to you, and you see the images. This is the only way. There is no other way. And you conclude that light bends. When it goes from here to here, it doesn't go in a straight line, but it goes in like this, ding, 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 like this. Okay. This is about the black hole, how it forms. You can read it. I cannot.